Now we're going to spend some time talking about sedimentation itself and the sedimentary structures that result as a function of the type of sedimentation that is occurring. As you can see here in Alaska, from stream footage, a multitude of grain sizes are being transported downstream, but at different rates, depending on their size and density. Now, sedimentary structures are all kinds of features that are formed in sediment at the time of deposition. There's a wide variety of them, as we'll see. These include bedding, which is also known as stratification, or the layering of rocks, cross-bedding, angular from the horizontal. These beds represent transport. Graded bedding, a transition from one grain size to another. And ripples. These are things that you can see commonly in road cuts and along highways in places like the Canadian Rockies that represent waveforms. And bioturbation structures. These are sedimentary structures that are generated by animals digging through the sediment. The animals are turbating or turning over the sediment. So first we'll take a look at cross-bedding. Here we have a diagram that illustrates a couple of locations for the formation of cross-bedding like this. In deserts, we can have this type of bed formation where a grain rolls or saltates up a slope forced by wind, and then it reaches the top of the dune here and slides down. Water will do something similar. These types of beds are asymmetric, and they imply some current direction, some dominant current direction, whether it's wind or water. So the wind or water is moving in this direction. The grains are rolling, bouncing, and sliding along in that direction as well. And if they're covered up by subsequent beds, they may be preserved in the rock record, as we've seen in Zion National Park in the cross-bedding of the Navajo sandstone, a Jurassic sandstone. Here we have an example of symmetrical ripples. These would be typical of environments where the movement is back and forth. The movement of the wind or the movement of the water is back and forth, back and forth. And this results in a stacking of sediment that forms a superficial expression that's symmetrical. And these asymmetrical ripples, again, are formed in environments where the current is more or less continuous in terms of its direction. And in the case of dunes that are preserved as rock, we can tell the direction of the current movement in the past. So we can tell which way the wind blew in the Jurassic from the orientation of the dunes in the Navajo sandstone. Here we have some examples of modern ripples. These are forming today, or at least the day this picture was taken in 2009 or so. And here we have an example of ancient ripples that are hundreds of millions of years of age. Again, the present is the key to the past. Now these may look like fossils, and they are in a way. They're ichnofossils or trace fossils. But what they represent is the activity of animals that were burrowing through this sediment. As they burrowed through here, their little appendages poked out and moved sediment away in a characteristic manner that allows us to define this structure as being generated by a particular organism. When we talk about sedimentary structures, we talk about bedding sequences. Bedding sequences are vertically stacked layers of sedimentary rock with different types of sedimentary structures in each layer. So these represent a changing environment. And in the case where they're repeated, like we see here, this bed and this bed look similar. We've gone from the conditions that produce this bed to alternate conditions, and then back to the conditions that produced this bed again. This may happen over and over and over again, tens or dozens or hundreds of times in a rock sequence. When we look at bedding structures as they're developed in a river system, we can see here the activity of the river being represented at a specific time. Each of these sedimentary features is being generated at the same time in this system, just in a slightly different location. So here we have the deep channel coarse grained sediment on the outside curve of a river where the water is moving fastest. And as we move closer and closer to the inside of the curve here, the sediment is going to become increasingly finer. It's becoming increasingly finer because the current is much lower in this environment than it is in this environment. Burial is the preservation of sediment within a sedimentary basin. It's dropped in a basin and it's covered up. It's buried. Diagenesis, on the other hand, again, is the rebirth, generally chemical rebirth. So it's the physical and chemical change that converts sediment to sedimentary rocks. More commonly, it's used to talk about a change in the initial sedimentary rock. So the sedimentary rock forms, and then it undergoes diagenesis. In the case of your book, it describes diagenesis as the physical and chemical change that converts sediment to sedimentary rocks. We'll use either definition in this case. Lithification, which means rockification, includes compaction, a compression of the material, forcing the grains closer together, followed by cementation, the growth of cement between the grains that holds them together. We can see that here in a series of diagrams. Starting with the burial and compaction, we have sediment working its way into this aquatic system, this water, where it's going to stack up. As it stacks up, more and more weight presses down on top, and that compacts and ultimately lithifies the rock below at fairly shallow depth and therefore relatively low temperatures. Diagenesis includes the processes, including physical and chemical, that change sediments to sedimentary rocks. So here we have an example of compaction. So we're forcing these grains closer together and we're squeezing out the water. There's less space here between the grains now. And this makes it easier to cement the grains together because this would require a lot of cement here as opposed to if we had a compaction like this, much less pore space that needs to be filled in this case with rhombs of calcite. Ultimately, we can crunch the grains together and force lithification, or we can simply allow the pore space to evaporate, the water in the pore space to evaporate, concentrating the calcium ions in this case, and forming calcite cementation, a very common cement in sedimentary rock. Different types of sediment are going to result in different types of sedimentary rocks. Starting with the very finest grain material, mud. If we compress this mud and cement those grains together, we end up with a shale. This is often clay. So very, very fine grain material in the case of clay-sized material. Sand, if we compress this material, we end up with a sandstone. So no surprise there. Gravel, a mixture of different sizes of material here, is ultimately going to be cemented together to form a rock called a conglomerate. In the UK, it's called a pudding stone. Pudding in the UK is different than pudding in North America. It looks a lot like this. These diatoms may be compressed together along with organic matter and heated, resulting in a conversion of that organic matter into oil and gas. The plant material from, say, a swamp may be compressed from that peat that you saw in the Ireland slides in the last lecture. Compress and heat that, and the result is coal. So here we have an example of a quartz sandstone. You can see the quartz grains here. And this colorful material, it's called pleochroic cement, is made up of little grains of calcite that are all grown together. Now, to classify sedimentary rocks, we're going to need to know something about the particle sizes that make up the sedimentary rocks. We're going to be classifying them, therefore, based on texture and composition. Now, if you're going into sedimentology, you're going to need to know this in considerable detail. For our purposes, we just need to know a couple things, and we'll start at the top here. Now, a boulder is anything larger than 256 millimeters in diameter. So that's going to be an important one. A pebble is anything between 2 millimeters and 64 millimeters. Coarser than sand, but significantly smaller than a boulder. That makes sense in our common usage. Sand is going to range from 0.062 millimeters to 2 millimeters in diameter. And that's going to be considered a medium-grained sedimentary rock. Finer grained material, such as silt, is something you can, if it's large enough, if it's on the larger end of the silt scale, you'll be able to see it with the naked eye. If you hold the rock in the sun, the little flashing, glittery bits would be silt. On the finer end, the best way to differentiate between silt and clay is actually by biting a little piece off and grinding it between your teeth. If it's silt-sized particles, it'll feel gritty. And if it's clay, finer than 0.0039 millimeters, it has kind of a creamy feel to it. So it's not going to be gritty. So smooth is going to be clay, which is why we use clay in things like ice cream and chocolate. Silt, no one wants that in their ice cream or chocolate. Definitely no sand, pebbles, or boulders. So things you need to know: boulders are bigger than 256 millimeters. Pebbles are between 2 and 64 millimeters. Sand is between 2 and 0.062 millimeters. And then silt and clay. Silt you can feel between your teeth. Clay you cannot feel between your teeth. The rocks that result are claystones, shales, and mudstones, defined based on the way they break. Siltstones made of silt, sandstones made of sand, and larger than sand, we call those rocks conglomerates. Some photo examples here is a conglomerate. It's a poorly sorted conglomerate. You'll see some angular grains here, some rounded grains, large grains, medium-sized grains, and small grains. So again, poorly sorted. The angularity indicates this is a relatively immature rock. Sandstone, in this case, a medium-grained sandstone. You can see some bedding features here within the sandstone that hint back to how it was formed. And then shale, made up of clays. Those clays are like playing cards. Clays are all going to line up, and this gives the shale its bedding characteristics. It splits along those bedding planes because the clay minerals are flat. When we talk about composition of siliciclastic sediments, we have 4 major groups. Arkose, which are made predominantly of feldspar grains. Lithic, these are made of grains of rock. So broken pieces of rock will form the grains in a lithic siliciclastic sediment. Quartz arenite is a very clean quartz sandstone. And a grey-wacky. This is a grayish, bluish, greenish colored rock. Wacky is German for trash or garbage. So it's gray garbage. This means it's made up of all kinds of junk, rock junk. Here we have the formation environments of these types of rocks. Lithic fragments. Again, these are going to be sandstones made up with lots of bits and pieces of precursor rocks. And you can see that here. Quartz grains represented by the gray. Feldspar grains here, and then rock fragments represented by the green. These are going to tend to form in environments like deltas. Arkose is going to be a feldspar-rich siliciclastic sediment that ultimately forms a rock called an arkose. And here you see quartz grains with interspersed feldspar grains. These can be almost entirely feldspar in some cases. Quartz arenite, nice, clean quartz siliciclastic rock. It has gone through the ringer a number of times. It has been deposited as maybe a lithic sandstone, weathered again, and by re-weathering it, you get rid of those rock fragments. It can start as an arkose, weather it again, you eliminate those feldspar fragments. A grey-wacky, again a junk rock, is going to tend to form off the continental slope and submarine fans like the Bengal fan. When we talk about biological sedimentary rocks, we need to use a different system. This system incorporates rocks such as limestones, cherts, limestones being made of calcium carbonate, chert being silicon dioxide, so CaCO3 for limestone, SiO2 for chert, organic material like peat, and phosphorite, rocks made up of significant amounts of phosphatic material, the bones and teeth of ancient organisms. Talking about chemical sedimentary rocks, we have rocks such as dolostone. These dolostones, also called dolomite, are calcium magnesium carbonate that is diagenetically related to a precursor limestone. So we had the initial deposition of aragonite, like in Belize and the Florida Keys and the Bahamas we saw earlier. After time, with some heat and pressure, we push some magnesium into the crystal lattice. It's not like high magnesium calcite, it's a new mineral called dolomite, calcium magnesium carbonate. This dolostone here is the result of a chemical change from a limestone. Iron formations are the result of a chemical reaction between iron in the anoxic state and oxygen. Evaporites we've covered pretty substantially so far in this series of lectures. This is what's left behind when the water evaporates. Classify these rocks, starting with the biological material. Sand and mud can be made up principally of grains of aragonite. Fine-grained aragonite, like coming from Penicillus, or coarser-grained carbonate coming from Halimeda, oatmeal flakes versus mud. And in this case, these are going to be calcium carbonate, the minerals calcite and aragonite. They're ultimately going to end up forming a rock that we call limestone. Siliceous sediment, which comes from diatoms and radiolarians, ultimately becomes a rock called chert, which is made up of silica. It's the same chemistry as quartz sand, but this has a biological source. The minerals that make up these types of rocks include opal, chalcedony, and quartz. These are all forms of SiO2. Peat and other organic matter may accumulate as organic rocks that are made up of various plant-based materials. This includes coal, oil, and natural gas. Phosphorites are made up entirely via the process of diagenesis. So again, we start out with a deposit of bones and teeth, perhaps. The basic chemical formula for the mineral apatite here is diagenetically emplaced in a precursor of sedimentary fabric. And again, the mineral is going to be apatite. Same thing the enamel of your teeth is made of. Chemical rocks that have no primary sediment include dolostones that we just discussed, iron oxide sediment that we also discussed, and evaporites. Again, dolomite or dolostone is a calcium magnesium carbonate. It's not high magnesium calcite, it's a different mineral with this formula. The iron silicates and iron oxides have a general formula of Fe2O3. Those minerals would be hematite and siderite. Evaporite sediments can be sulfates and halides. So gypsum, anhydrite, halite, and other salts are what's left behind when the water goes away. Just some examples here. We have a finely bedded limestone. Calcite and aragonite were the precursors. Aragonite is almost always converted into calcite by the time the material becomes a limestone. Chert. This is an example of a chert nodule, and this is what it looks like inside. This is also known as flint and jasper and all kinds of other names. Usually every other year or so, somebody brings something like this into the department and they want it identified. What kind of bone is it? So one year I had a guy bring something like this in and he said, "What is this?" And I said, "It's a chert nodule." And his response was, "You don't know what you're talking about. I'm going to find somebody that knows what they're talking about." I said, "Okay, good luck." And we have gypsum, calcium sulfate with some water, a very common evaporite mineral. Halite, also a very common evaporite mineral. These are cubes, modified cubes, that are known as hopper crystals because they look like a hopper, or as you'd say in Boston, a hopper. Organic reef development, we talked about this in previous lecture. We have environments like this, the Great Bahama Bank, Little Bahama Bank, Florida Bay, Guantanamo Bay. We showed some pictures of Belize and Palau. These are reefs that are built in warm, shallow seas by organisms that precipitate calcium carbonate. Again, predominantly algae, but corals are important as a framework as well. Moving into the Central Pacific, we can see this type of feature develop. This is when a volcano subsides after cooling. And the result is we're going to have a coral reef form around the volcano. The volcano sinks, producing a lagoon, which is going to be a very different environment than that right here, adjacent to the lagoon. The coral reef is going to continue to grow upward as the volcano sinks. So we're going to see an accumulation of carbonate around this feature. Eventually, this can be a pretty significant feature. It looks like a giant carbonate tree stump in the middle of the Pacific Ocean. And at that point, we call it a guyot, G-U-Y-O-T, these tree stumpy carbonates as they persist in the Pacific. The Marshall Islands would be a good example. And, of course, Bora Bora is a very good example. So we can see what's left of the volcano here in the center. It's going to sink away, forming a big open lagoon that's going to fill with carbonate. On the outside, the carbonate reef is going to grow, keeping up with the sinking of the rock that it's fixed to. We can have rudists. These are ancient organisms that make up the reefy structures of the Permian of West Texas. That's where the cheap, easy to get at oil is located. It's in these kind of rudist rocks. One thing you may not know is that these kinds of carbonate reefs can grow in lakes as well. This is a lake that's located about 15-minute drive from Syracuse, New York. And what you can see here is a carbonate reef that's growing into the lake. It's not being produced by corals. It's not being produced by algae. It's being produced by bacteria. Senecococcal bacteria grow calcite on the outside of their little bacterial bodies, and they form what's known as a thrombolytic microbialite, which means a blob-shaped thing made of microbes. And just another photo here. The water that the bacteria use to produce these structures is calcium carbonate rich, particularly calcium ions. So when that calcium-rich water hits the lake, the bacteria precipitate calcium carbonate, and this structure grows out into the lake. This is a very deep lake for how small it is. 10 times the size of the bowl outside of geology, and it's about 53 meters deep. So it's a soup can-shaped lake. Examples of carbonate sediment and rocks include limestones, dolostone, whereas evaporate sediments and rocks include marine deposits and non-marine deposits. So here are a couple photos of westernmost Europe. This is the Rock of Gibraltar. I'm hanging out with a Barbary ape here, and in the background is the Straits of Gibraltar. Africa is right here in the clouds. So took the boat over to Africa. This is standing in Morocco with the Rock of Gibraltar back here in the clouds. You can see the large number of ships moving in and out of the Mediterranean Sea via the Straits of Gibraltar, also known historically as the Pillars of Hercules. So we have a very narrow inlet to a very large intercontinental sea, Mediterranean, in the middle of the land, sea. So fairly deep as this water comes in. When the Mediterranean was relatively dry, it goes over a waterfall. It works its way through the basin here and evaporates. As it evaporates, it leaves behind gypsum and halite crystals, enormous amounts of gypsum and halite crystals. Now, during World War II, the Nazi Navy used this characteristic. The Mediterranean was full, of course, in that marine water would slide into the Mediterranean, work its way across the Mediterranean to just off the coast of Lebanon here, and evaporate. As it evaporates, it becomes denser, it sinks, and that dense salty water works its way back out into the North Atlantic. So the lower currents move this way, the upper currents move this way. So the Germans learned they could turn off their diesel-powered submarines and slide in the surface water without the British seeing them from the Rock of Gibraltar and do their thing in the Mediterranean. When they wanted to sneak back out, they would drop to a lower depth and turn off the motors and just slide out with the current back into the North Atlantic. The result of this in ancient times was thick sequences of evaporite minerals. This is known as the Messinian salinity crisis. You don't have to know that. Other types of sediment and rocks include siliceous rocks, phosphorites, iron oxides, and coal and peat.